This video might have part 1, 2, and 3, right, for that little clip if I even got it. Okay, so we move forward in slides, right? And so this is still the one-way slab, even though it has a crisscross of beams. Okay, and so if we look at this carefully, right, we have our column that's supporting our long beam here, which would be called a girder. And so the use of girder and beam is somewhat interchangeable, right? Girder is always the largest, right? Beam would be the next size down. Joist would be the next size down, right? It just works in that order, though oftentimes you'll refer to something like a girder and call it a beam, right? So they get a little bit confusing, but I just want you to know the general order, right? So in this particular case, that would be the girder, right? Right? These pieces here are the beams, right? They are resting on top of the girders, right? Then the slab, right, the floor, is spanning between the beams. Yeah. Concrete. Everything's concrete. Everything's concrete. Well, all we're discussing is concrete. So everything's going to be concrete and stay concrete, right? We'll get to steel and wood and that kind of stuff later on, and it's very different and distinct. Okay? So if we're looking at a column to beam connection or a column to girder connection, this is not the type of rebar that I'm going to make you memorize like where it goes, but I want you to look at how much rebar is in this kind of a connection, right? Because we're transferring a lot of vertical load resting on this beam into the column and then down the column, right? So it takes a lot of a connection. Furthermore, this is also a point where we've got lateral loading, right, from wind, from earthquake, and that kind of stuff, having to transfer into the column without buckling the column, right, which is why there's so much steel in this type of a connection. Okay? Yes?
So does that mean that it's the strength depends on how wide it is?
It depends on how deep it is.
Oh, how deep it is.
And they're saying that typically a beam is going to be 2 or 3 times as deep as it is wide. Right? So by breadth, they mean width. Right? So a one-way solid slab system is going to span across parallel lines of support, right, which I've said several times, right? The walls and the columns are going to be poured prior to the slab, right? But forms for the girders and or the beams are going to be poured at the same time as the slab. Okay? So vertical stuff is poured first, then all of the floor level is poured, okay, including the beams and the girders. So the forms for the girders and the beams are put in first, then the forms for the slabs are put in. Right? Recognizing that the whole thing is going to be poured at one time, right? But we start with the beams or the girders, right? The forms are supported by temporary joists and beams, right? The joists and beams are supported by shores. Shores are just the vertical pieces that support it, right? And they're adjustable in their length, and they're going to vary a little bit in look, right? So in this particular example, recognize this doesn't have to be perfectly precise. Right? We're just looking for general support for the slab. This would be a slab, right? This is the formwork that would be on the underside of the slab on a second floor, right? Our joists are these smaller pieces here. Our beams are the larger pieces. This is one of the shores. It has an adjustable screw top to it, so it can adjust how far it is from the ground, right? Depending on how many shores and beams and joists you have above it, it can adjust. This particular one has a second side over here. They don't necessarily have 2, right? It might just be 1. It depends a lot on the formwork. So here it is, looking at it a little bit closer. Here's that screw, right? That's the adjustable part that would be supporting the beam, right? Likewise, we have it over here supporting that beam. Okay, so if we look at it at a larger scale, right? This is the top surface of a slab that's going to be poured, right? Notice there's a fair distance. This is a pretty tall ceiling, right? They've already poured the support lines, the walls, right? This is just the deck, right? That's the support for the concrete slab. These are all the little joists, and they're stacked up going back this way, right? That are then supporting the plywood, right? Below that, we have our beams that are running the opposite direction. Below that, we have our shores that are supporting that, right? Recognize we have to support a fair amount of weight, right, when we're pouring that concrete, right? And so due to that weight, right, the temporary stuff, right, the shores, the beams, the joists, all that stuff, tend to be really densely packed, right? Once the concrete cures, it can span the distance by itself. But when concrete's in its uncured state, it's very heavy, right, and doesn't have any structural support whatsoever. So we need a lot of extra support to support it so that it can cure in its proper place, right? The other thing about the formwork is generally on a big building like this, the formwork is going to be designed by the structural engineer, right? So they're going to specify where does the formwork go, how many, right? How many shores, that kind of stuff, right? How large should it be? What kinds of spans can it have, right? And then the contractor is going to be responsible for just building it based on what the engineer tells them to do, right? The edges tend to have beveled spacers to reduce chipping. So it's very rare when we have a nice sharp corner, right? Generally on the bottom of a beam, if you go into a parking garage, look up and you'll see this, right? Generally every beam or girder has a chipped corner, right, or a chamfered corner because it's easier to remove the formwork. You don't have an edge that accidentally gets chipped and then looks bad, right? So after the formwork is constructed, the reinforcing is assembled on top of it based on whatever the structural engineer's requirements would be, right? And then after that, you've got the bottom bars, the top bars, the stirrups. Those are all installed for the girders and the beams, right? Again, chairs as necessary, right? And we'll see this just in a second, right? Then the slab reinforcing is placed on top, right, and tied together with the girders. Remember, it's all going to be poured at once. So we do the girder reinforcing, then we do the slab reinforcing, right? And then a typical slab is going to be somewhere between 4 and 10 inches, right? Obviously, if you're in a parking garage, right, thicker slab, more weight, right? If you're in something that's residential, maybe you can shrink it down, right? It's also dependent on the length of the span, right? How far is the span? The longer the span, the deeper the slab, right? It's finished in exactly the same manner that we talked about doing a slab on grate, right? Which was screeding first, floating, troweling. Nice. Okay, so looking at it a little bit here, right, on a construction site. So in this particular example, right, it's hard to see through this a little bit. By the way, what's the green tell us? It's an epoxy coated, so it's in somewhat of a toxic environment, right? So we want to be aware of toxic, not toxic chemicals, toxic salts, that kind of stuff, right? Okay, but if we look really carefully underneath, right, this mesh of reinforcing, we can see the bottom surface of the slab, and we can also see, right, the beam or the girder being formed out that would go down in this depression, and it comes back up and is there. I think I have a couple more examples here in a second. Okay, so this happens to be stainless steel rebar, similar use. It's somewhat toxic, right? So we've got our formwork, right? This is our underside of the slab, right? Notice the bevel or the chamfer, so that we don't have that chippage that we were talking about, right? Then we come down into the girder, right? We place the reinforcing into the girder first, and then we'll tie this reinforcing into the reinforcing that's part of the slab. Okay? Notice the chairs that run all the way along the bottom, right? Keeping that a nice even distance from the bottom of the beam or the girder, right? They're also using chairs on either side to make sure that that stays its correct distance, right? And so if you think about trying to do this, this would be a lot easier if you put these continuous chairs, right? You tie it up on the top surface, then you lower it down into place, and you know it's in the right position. Yeah. No, it refers just to the fact that you have two lines of support and the slab spans in between. So in this example, the lines of support that would make this a one-way slab would be this girder, right, and the girder that would be over here. And the slab spans between girder and girder. Exactly, right. So we have one line of support here, one line of support here, and the slab is going to span between those two lines of support. Exactly, but it's going to be, there's going to be distance in between, but yes, it's going to be exactly like that. Right. So it's going to, this slide, right, is the same as this, right? Where we have a girder here, we would have another one here, and the slab is going to span, right? So we were looking at the inside of this little girder on that slide. So we're going to get to a two-way, right? We're still in the one-way slab. That's still a one-way. Okay? So if we're looking at from the top, right, this is after the reinforcing has already been put in, right? We notice that there's a girder or a beam that's right at the edge here. This is like an opening for a stairway, right? But this shows you the rest of the reinforcing that's tied in, and then they'll pour the concrete on top, finish it the same way. Okay? So, when the slab beams and girders have achieved enough strength, when they've cured enough, right, to be somewhat self-supporting, they'll remove the bulk of the shoring, right, the bulk of the formwork, expose the underside of the surface of the building itself, right, and then they'll come in and they'll reshore, right, with a few shores to help support it while it continues to cure, right? So we get the bulk of it there, but we pull as much of the formwork down as possible because guess what? We can move up a story and start the process over again, right? But we're going to continue to reshore with a few extra braces and a few extra shores to make sure that the concrete will stay in roughly its position, right? Which it should, but it needs a little extra support, right? So that's going to take a full 28 days before you're going to pull those down, right? So generally speaking, the larger the span, the thicker the slab, right? That's going to be true no matter what building material we're using, right? Whenever you do a longer span, thicker it's going to have to be, okay? If the spans are too large, right, we can remove some portion of the concrete. So let's imagine for a second, right, that we keep wanting a larger and a larger span, and we'll keep adding to the depth, right, of the slab, right? Let's say we get up to 2 feet deep of slab, right? That's going to start to get really, really heavy, right? We want the depth of the 2 feet to get the span, right? But it's too heavy. There's too much concrete. It's going to weigh too much. So what do we do about that, right? We can actually remove some of the non-working concrete, right, and create a one-way concrete joist system, right, which will make more sense in a second, right? So before we get to the joist system, right, we can put these slab bands on top of the parallel lines of support, which is basically widening it up. But again, this is still adding weight, right? But we can get into this, right, which I'm going to jump ahead and show you the 3D model because I think it's a little bit clearer to see, right? So in this particular example, right, we have a parallel line of support here, right, and there, right? But we want to span between these two lines of support. They're far enough away to where we need some significant depth, right? And this usually starts in the realm of 18 inches, 2 feet, something like that, right? But if we had a 2-foot thick slab, it's just way too heavy. So what do? Right? We need the depth, but we don't need the depth continuously all the way along, right? So we scoop out the non-working concrete in these voids and create these voids, right? And allow these thinner little ribs to span, right? It's still one slab, right? We've just taken out some of the concrete in the slab, okay? And so if we look at the actual plan view, right, and section view, right, in this particular example, right, this is the void that we're cutting out, right? There's a void that we're cutting out. This is the beam that's providing the support. This is the other beam that's providing the support, right? And this is the slab that's spanning between those two lines of support. If we look at the section view, right, there's our thin slab, right? And there's the bottom of that cavity, right? The bottom of the joist, so to speak. So how do we make this? Okay, we use a special type of formwork, right? It's going to be a metal or plastic pan, right, that we sit upside down, right, on our particular. So we make up our formwork with our normal base, right, our normal plywood. Then we put these pans upside down, right, and they're somewhere to 20 or 30 inches wide. The sides of the pans have a slight slope. I wish I had one here. It's one of the few things that we don't have in this room, right? They have a slight slope to them, right? And then we pour the concrete around them. And I think the next slide gives kind of a 3D view of that. Yeah, I'm going to go back to the slide with the text on it, right? So we put these pans in place, right? And then we can pour the concrete in and around these pans to provide those little ribs. Does that make sense? Yeah? Okay. So a distribution rib is often at the midspan, right? So that's what they're referring to. Hold on one second. Right? It's this little rib here. So this non-working concrete, right, could go all the way through, but that little distribution rib just helps if you have some kind of a point load. If you put a desk somewhere, right, you're helping to distribute that load out, right? So that's called a distribution rib, right? And that occurs at the midspan, right? They're supported by what are called joist bands, which are just wider beams, which you can see, right here, right? So we don't need a girder underneath it because we're already having all that depth in the slab. We just have a much thicker little slab band here, right, that attaches to our columns, right? Then we have our joists that run across, right? And so while a deeper beam would be stronger, right, it would be more economical to form them at the same depth, right? So this, if you think about the formwork for building something like this, it's really simple because you have the column come up, and then on top of the column, you just build a big flat sheet, right? And then you build this whole slab system on that flat sheet. So there's not all the formwork of doing each of those individual girders, right? So it ends up being more economical to build something like this from a formwork standpoint, right? Which is one of the big advantages of doing this. So if we look at this example again, right? We have each of these little domes that have been placed in, right? We're running our reinforcing in between. Now this has slightly different reinforcing in it, which most of you might recognize from earlier on that these are little post-tensioning cables that have been put in, but you get the idea nonetheless, right? The reinforcing would go there. Up at the top here, you can see faintly the welded wire reinforcing that's going to run in on top of this system, right? There's also gaps in between, so this would be the slab band, right? This smaller gap would be that distribution, right, joist at the middle, at the midspan, right? So this is just the 3D view, right? This is the temporary shoring. Here's our concrete that's going around one of these little domes. In this particular example, it's a proprietary system where they're forming it up. The dome is part of a styrofoam form that makes these cavities. But the idea is the same thing, right? So I always like to show the architectural example of how you can be playful with these concepts, right? Best example would be the Sydney Opera House. It has these kinds of joist, one-way joist systems in it, but they've taken, right, what would be a normal cavity formed here, right, and they've splayed it out so it gets wider and thinner, right, which gives a certain texture to the ceiling, right? So they're, again, playing with the concept by changing what the domes would be, right? So we can move, those were one-way systems, right? We can move into what is called a two-way system, right? And a two-way system is different because it's spanning in two directions at once, right? And so the first example of this would be a two-way flat slab system, right? And what you're going to have is you're going to have either two parallel lines of support or most likely 4 columns that are in a square, right? Not a rectangle, a square, right? And those 4 columns are going to provide the support for, right, one set of slabs. So if we look at this, right, we have a column, a column, a column, and a column, right? Those 4 columns are providing all of the support for this slab, and the slab has to span in this way and in this way, right, and diagonally that way. Does that make sense? So it's spanning in 2 directions at once, okay? And I think the next slab, yeah, this shows it a little bit better, right? So we have our support points, right, and the slab is spanning between support points this way and between support points that way, right? Two-way slab, 2 directions, right? Always square, always a square bay, right? And so in this particular example, it has mushroom capitals, right, which are just widening the top of the columns to help distribute the load, right? So the formwork is completely flat except for the column capitals if you have them, right? Not all buildings have them. It just depends on what kind of lateral loading you might have and how you want to try to transition or tie the column into the floor that's above, right? So if you're up here at the top, right, this is lighter loads, residential type stuff, right, where you don't have too much loading, you don't have too much lateral loading. You can get away with this where it's very clean to a slab, right? If we come down here, right, this is called a drop panel. right? It's a little bit of extra concrete around the capital or around the column, right? It's a heavy load, right? And then finally we get down to the very heavy load where we add the mushroom capital. And you can see that if we're looking at this in section, there's a lot more concrete that helps to transfer a load that would be coming horizontally down into the column, right? That top one would be much easier to break off, right, than the bottom one. Okay, so depending on load, you're going to vary the column capitals a bit. Okay, so in a two-way flat slab system, right, the typical depth of the slab is going to range somewhere between 6 and 12 inches, right? Most of the reinforcing is going to occur in the zones of the slab that cross the columns, right? So wherever the column lines end up. So if we had 4 columns, right, wherever we cross at columns, that's where the bulk of the reinforcing is. The least reinforcing is in the center of the slab, right? In that case, the center of the slab, it would be at the bottom of the center of the slab, right? The middle strips have lighter reinforcing, right? So this is our two-way flat plate, simple as it gets, right? Which is basically that example there, right? For the most part, right? There's a little beam in behind. Part of the problem is you pick examples, and I'm going to show you an example in just a second. That's a two-way flat slab system, except that there's an exception and there's a beam in it. You know, so a lot of times it is somewhat mixed, and you'll get more than just the classic example, but it still exists, and it's important to kind of show it, right? So two-way flat plate, no column capitals, right? The columns can be moved off the grid, right? It's hard to do it too often, right? And so I'm speaking primarily to the designers out there, right? But you know, certainly moving a column can be advantageous if you're trying to, but you have to be somewhat within a normal range. You can't move it too much off grid, right? Because the span changes, and then it's not a two-way slab anymore. It's 2.5, right? So you have a longer span in one direction. It's great for hotels, hospitals, dormitories, apartments, that kind of realm, right? 5 inches to 12 inches thick, right? It should have a cantilever on the exterior of the span of at least 30% of the span, right? And so the reason that this happens, and I'm going to draw this for just a second, right, to help illustrate this point. Okay? If I have my floor, right, and I have my column happening here, right, and we have another column here, and we have over here, we have another column here, right? Right? If I end my slab here, right, I've got a bunch of weight pushing down here that's going to want to bend this column over on the outside edge. But if I put 30% out here, right, so that's 30% of this, right, there's a bunch of weight that happens out here as part of the floor that helps balance out the fact that it wants to curve in. Does that make sense? Just from a conceptual standpoint, right? So typically on this kind of a building, which is a very modernist type building, right, you're going to have this bit of an overhang on the outside, right, to compensate for, right, the fact that it's a two-way flat slab system, right? Now, of course, architects love to do stuff like remove that. So, good example. Probably seen this before, right? Villa Savoye, Corbusier, right? And so we have some great examples of what I was talking about, right? So we're over here, right? This is a perfect, right, grid, two-way span, right? We've got the 30% overhang. Everything's working the way I was talking about. And, of course, then we move over to this side, and it doesn't have the exactly what I was trying to illustrate. But architects like to do that. Then we come in, right, and we see that, well, wait a minute, there's a few extra little beams that have been put in. And so it's not always perfect, right? But there are pieces of this building that do fall under the perfect category, right? So it is what it is, but that was a good example, right? Okay. So because there is no column capital, right, in this two-way flat plate system, we have a lot of what's called shear stress right at the joint between the column and the slab, right? And there's not a lot of concrete in between those two. So we use this special thing, right, that are called shear studs that help to transfer the stresses that are in the slab down into the column, right? And basically what these are is a strip of metal that has these giant nails that are welded to it, right? And so these giant nails help to add surface area and help to really attach the column to, right, the slab itself, right? So these strips are then attached to the column, right? They're welded to the rebar in the column, right? And that helps tie the two together, right? And so those are called shear studs. The examples in practice, right? Welded to that steel. Here we are, right? With the formwork itself, the columns coming up through. You see the vertical bars of the column right up here. These are the shear studs that are then going to attach to the slab, right? And those are going to help transfer any kind of weird lateral loads that happen on the building down into the column rather than breaking, right, between the slab and the column, right, causing it to collapse. Yeah. Say it again. Exactly. So they'll be completely covered by the slab. So in this particular example, right, those are sticking up 6 inches. The slab's probably going to be 8 to 10 inches thick, right? So they're going to be completely covered. But that's what's going to allow us to transfer some of that lateral load, right, down into the column, right? So just like we talked about in a one-way system, right, the longer the span, the deeper the slab, right? Two-way system works the same way. If we end up with too deep of a slab, right, we'd like to remove some of the non-working concrete, right? So we do the same thing that we did with the one-way joist system, only this way it's called a two-way waffle system, right? No surprise it's called a waffle because guess what? It looks like a waffle, right? So how many people have been to the library here, right? Did you notice anything about the ceiling, right? It's this, right? So this is very, very common. The architecture building at Berkeley, waffle slab, right? Very common because it's very economical, right? And so it's two-way system, right? Roughly square spans, same thing, right? 4 support points, right? And we're removing the non-working concrete, right? Notice that all of these are squares, right? That helps to tell you that it's a two-way system, right? And then we have these little joists that run in both directions that help us to span. This is the sectional view, right? This top one is at the column, which is just telling you that we have a full solid set, right, around. It's basically the capital to the column, right, to help transfer the load, right, which is right here, right? If we're at the midspan, right, we're going to carry these, right, all the way across, right? So let's see it in 3 dimensions, right? This is what I'm talking about. So the waffles here are going to be continuous on the interior. Around the tops of the columns, it's going to be solid, so we won't take those voids out. We'll have a little bit more concrete to help transfer any kind of lateral loads down into the columns themselves. Okay? So domes are used just like with the one-way joist system. This time they're square. Same rules apply. They're typically at least 18 inches deep, right? Somewhere between 18 and 24 usually. They have tapered sides, rounded corners so that they can pull out really easily, right? Because obviously if you have the formwork and you have the dome sitting on top of the formwork, when you take the formwork down, you have to get the dome out, right? And so it has to be in a manner that can get it out, right? Generally speaking, the joists, right, that run in both directions, right, are 6 inches wide and they're on 36-inch centers. That doesn't mean that all of them are, but that's generally speaking what the domes are going to look like, right? They could be a variety of depths up to 20 inches, okay? Solid concrete heads are left around the columns, right, by just leaving the domes out, right? Not too hard to do. Sorry for the blurry picture or the slightly old-looking picture, but the point is it still exists. Obviously, this is not some kind of fancy new post-tension slab, right? This is our very traditional, but we see very clearly each of these domes that's been laid in, and we also see very clearly the rebar running in both directions, right, through and around those domes. And this is what the resulting ceiling looks like. Now, again, every time you show an example, there's always exceptions, right, because people do things differently. In this particular example, we don't have the solid pieces around the column, right, but that's okay. We don't have to have them, but typically there would be the solid pieces around the column. And architects can do things like you can embed the lighting inside the ceiling and that sort of thing. The other thing that can happen is you can cover this up with some kind of a drop ceiling so that you don't even see that it's there, right? But it ends up being fairly economical, and it tends to end up being exposed, right? And so another example here, obviously this building is in the middle of being demolished, but you get the idea. You can see very, very clearly, right, the seams for where the domes used to be, right, where they sat down, right? And so you can see all the remnants of that sort of thing. Notice on a ceiling like this that all of the services for the building, the lights and the electrical and the smoke detectors and everything else has to be exposed. It's not something that can be easily buried into the slab, right? You can certainly run wiring and stuff inside of these, but it's always a little bit more challenging when you have these domes and you're planning on reusing them, right? You don't want to break those if you can avoid it, right? So the other option that we have, and we talked a little bit about this earlier, we talked a little bit about this last week, is the idea that we can post-tension a framing system, a concrete framing system. And so this is a form of pre-stressing concrete, right, like we talked about last week. But this tensioning is done after the slab has had a chance to cure, after the beam has had a chance to cure, right? And so what we do is we can put our tendons in desired locations, right? And I have an example of a tendon up here. This is the tendon, I'll pass this around, that doesn't have the plastic sheath on it, right? So you can see what that is. And I have over here, hold on a second. Right, I think this is the not so nasty one because it doesn't have the goo on it. So you can see the plastic sheath and the tendon itself, and pass that around. And so the nice thing about this, right, is that we can deliberately drape the tendon so that the reinforcing is at the bottom at the midspan, right, and at the top at the column, right? So we're using this more efficiently than we could normal rebar, right, because it's flexible like this, okay? So in practice, what does it look like, okay? So we look at something like this. Notice there's much, much less rebar in here as a whole, right? In this particular example, right, it's a one-way system, right? We can tell that we have a girder here. Our primary spans are in this direction, right, between girders. We've got reinforcing in the girder, right? But across the top here, right, there's our tendon, right? And generally when you look at something like this, there's less reinforcing because you have this tendon in there, right? So it drapes. It's at the top of the slab here. It droops down into the bottom of the slab at the midspan. Okay? So in terms of selecting which site cast framing method to pick, right, the first thing that you need to ask yourself is, are the bays square or not? And so by bay, right, I mean the distance between, right, the supporting lines. Okay? If we have a long rectangular bay, right, that's two parallel lines of support. It's going to be a one-way system, right? If we have a square, right, we have four columns that appear on a square, right? Those are going to be, right, a two-way slab system. Okay? The next thing is, how long is the span going to be, right? If it's 25 to 30 feet, we can end up with a two-way flat slab system. If we need longer spans than that, we have to be in the one-way system, right? So if you think about the grid of columns in a building, right, if they're square bays, right, you will have to make sure that those bays aren't any more than 25 to 30 feet in size, right? So we have limits in terms of how much we can span with a two-way system, right? With any option, if we do post-tensioning, the amount that we can span goes up. Yeah. If it's post-tension? Well, on a two-way system, you're going to max out at about 30 feet, right? If you add the post-tensioning in, if my memory is serving me correctly, which I should look up just to double check, it's usually a third longer, right? So we go to 45 feet, right? But again, it depends on the engineer and the calculations and stuff, right? And I should double check that number because that's off the top of my head, right? Yes, sir. It's because of the weight, right? So even if you could keep increasing the depth, it starts to get so heavy on those 4 columns that you just can't get a further span, right? You need the grid of columns because you can't have any girders or beams, right? That's the nature of the two-way system that doesn't exist, right? So the next thing is how heavy are the loads, right? If you have industrial loads, guess what? Thicker slabs, right? If you have commercial or residential or something like that, right, you can have thinner slabs, right? Therefore, you have a lighter weight system, right? Do you care about what the underside looks like, right? If you're going to have a drop ceiling, right, that's going to hide your electrical systems and whatever else, you can get away with a waffle slab or something that you might consider to be uglier because you're planning on covering it up, right? And so that's the other thing to really think about, right? And so the last thing is, are you in some kind of an area or a zone that's subject to a lot of earthquakes, right, and those types of conditions? If you're in an area that's subject to that, you have to pay a lot of attention as to how are you going to connect the column to the slab and how much concrete and how much reinforcing is it going to take to make that a stable system for an earthquake environment, right? So, for example, if I was building something, we'll show you this in a second. If I was building something, here in California, I'd be very nervous of, a flat plate, a two-way flat plate, if it had any kind of major loads on it because of this earthquake condition, right? So let's say I was building a skyscraper. I'm on 221 and I'm designing my skyscraper. I would stay away from the flat plate system because there's not enough depth to transfer the loads, right, that would be acting on a particular building down into one of those columns, right? So that's kind of one of those things you want to be thinking about, okay? So the other thing about concrete that's important to recognize is that if you're ever doing retrofit work on concrete, it can be very, very challenging. So you have to plan ahead in concrete if you want anything to be run through the concrete, right? So if we're going to put electrical in, if we're going to put plumbing in, right, all that stuff has to be planned ahead, right, because you can't go cutting into a slab. We talked at the beginning of class today about if you're in one of the newer houses, right, where they built the slab and post-tension the slab, right, even though it's a slab on grade, they put those post-tension tendons in, right, and they tighten it up and they put those stamps on the floor that says don't drill into this slab, right? If you want to drill into the slab because you want to, say, convert a half bath into a full bath and add a shower, right, you can't drill into that slab to bring in your plumbing or to put in your waste because that system, right, because it has those post-tension cables in it, right, you could damage the overall slab. You could end up nicking one of the cables, causing it to fail and shoot out the building. Total side story because it's kind of interesting, and I just mentioned that. They were doing some post-tensioning on a building in Berkeley, and they had gone up. It was on a second story, and they needed to tighten the tendons for the first time, right? And so when you're tightening these tendons, right, and this is we'll go back and forth and cover this stuff, right, later on, right? You're pulling on the ends of these tendons, right, and then you're applying a plate like this with a little wedge that goes into place, right, and that's going to then hold this tightened cable, right, against the edge of the foundation, right? But when you're pulling on this, if something were defective about this particular piece, you're putting an incredible amount of strain on this piece of metal, right? So if something like this were nicked, right, and you were pulling on it and you were putting that kind of tendon and it broke, right, this is the kind of thing that could shoot a couple blocks in a direction and cut through a building, right, because it's a very long tendon. So in this particular example, they were going to post-tension this building in Berkeley, and they actually evacuated the neighboring buildings because they were afraid that one of the tendons would break, right, during this process. Once it's in place, right, and the caps are on and everything else, it works fantastic, right? But you have to be really careful. So if you live in one of those new houses that has those do not drill into the floor stamps, right, this is the kind of thing that could happen if you started drilling into the floor, right, because you'd relieve that stress that's holding the whole slab together, right, and cause the tendon to shoot out one end or the other, right, damaging your neighbor's property and that sort of thing, right? So anyway, if you're ever in the construction process where you're trying to do a retrofit, and I like this video because it kind of shows you the example. This is one of me 3 or 4 years ago. We were doing this. It was the same remodel in Rossmore that I had to put the floor stuff down. And we decided we were going to add a full bath where it was a half bath before, so we needed to cut in for new sewer lines and new plumbing, all right? And so this is a slab on grade. 4-inch thick slab, followed by the pea gravel, followed by the moisture barrier, followed by the capillary break, exactly like we were anticipating. And below that, we had to dig down about 4 feet to get into the sewer line, right, which happened to be relatively close. So we were somewhat lucky to where the position of this particular shower was. So anyway,
go.
You don't have particular.
So here we go. We're about to cut through the slab floor
here.
here.
You get the idea. So this but you can kind of look at the giant disaster that this is going to happen. That would
Quite
be where
the mess.
humanity would be.
So now we just have 2 more sides to go.
Right? It's pretty much a giant mess. Right? So after you do that particular piece, right, then you have to take a sledgehammer, break out that piece of concrete, right, remove that, you dig down your 4 feet, tie into the new sewer line, right? Obviously, you have to have the inspector come out and verify that you tied it in correctly and you glued it in correctly and all that kind of stuff. After that, you backfill around your pipes, right? Then you drill into the sides, right, that you just cut and removed. You drill into the sides. You put in your rebar. You put in epoxy to reestablish the grid of rebar that's reinforcing that particular piece, right? Then you go ahead and you put in a new moisture barrier. Basically, you reverse the whole process all the way up, right? You pour your slab, and then finally you can start with your new shower, right? So the point behind showing this video and giving you a little bit better understanding is that concrete is a very permanent thing, right? If you have a wood-framed house, you have a crawl space underneath, you want to do a retrofit, it's not that big a deal, right? You have access to your things, right? You have access to your building services. If you're in a concrete foundation, right, you have to be much more careful about making sure the stuff is where it is before you get to the process of having to do it, okay? So we shift gears a little bit, right, into a variant of site-cast concrete. It's kind of a hybrid between precast and site-cast. It happens to be some precast elements that are cast on site, right? And that's tilt-up construction, right? And so what we do is we pour our slab on grade first, right? And after that, right, we pour our wall vertical pieces flat on the existing slab, right? So we use our slab on grade as one side of our formwork, right? So instead of going through the work of building one wall up, right, putting all the form ties in, and then building the second wall up and then pouring in between, right, we use the ground, right, our freshly poured slab as one side of the formwork, right, and then we build a simple edge form like we did in the very beginning that goes around the outside of our building, and then we pour the next piece, right, and ultimately once that cures, right, we can tilt it up, which is hence tilt-up construction, right, we can tilt up that wall section into place, right. And so we use a crane to actually get it up into place. So here's our examples, right? Here's our perimeter edge form right there, right? Obviously, some of this kind of stuff concerns me. We've got all this water. That's not a good thing, right? Hopefully it dried before they decided to pour the concrete, right? So they lay out these forms, right? And then these are ultimately going to be the walls that you're going to tip up into place. They'll spray a form release agent to make sure that they separate. Absolutely. Right? So it's incredibly economical, right, for buildings with a large floor area, right, that are relatively short, right? You wouldn't be able to do this for, say, a skyscraper, right, because there's not enough surface area on the ground to be able to tilt up the wall correctly. So you need a wider building than it is tall, right, for this to work. So like a Costco or a Fry's or something like that, right? Those would be the kind of the realm of this kind of thing, right? Industrial warehouse type buildings, okay? Typically, your building height or your panels are not going to exceed 45 feet, right? That's about the max on this type of construction, right? So after you do your perimeter edge form around, right, then you go ahead and lay in your rebar, right, that provides the primary tensile support in your wall. Now, part of the challenge of this is your wall isn't in its vertical position yet, right? It's laying down, and you have to get it from being laying down into its vertical position. And so you have to do a little bit of extra reinforcing to allow you to pick it up and get it into position, right? So if we look carefully here, we can see here some of the hooks right, that the crane will attach to, right? And so there's extra rebar around each of those hooks, where if you were building a wall, you wouldn't need that extra rebar. You wouldn't need that extra reinforcing, right? So it's slightly different in terms of how you do the reinforcing for it, just so that you can lift it up into place, right? So here we are, right, where we've gone ahead. We have the perimeter edge form. We've poured the slab. Notice that you can finish the surface of the wall just like you would finish a slab, so you can get a very smooth, nice finish. No little form tie cones that you have to grout, right? It can be a really nice surface, okay? You do that, right? You make that nice surface, okay? In this particular example, they've attached these temporary braces to it, right? We also have our hooks that are attaching to the crane, right? The crane lifts this wall into position, right? It carefully guides it into position. You've got the people trying to guide it there. Then they attach these temporary braces while they grout the joints between them, right? They try to tie the whole building together. Now, this building is not particularly stable until you get the roof structure across the top. And we're not going to talk a lot about roof structure until we get to steel, because most of the roof structures are steel, right? So just trust me that there's a roof that needs to go on to make this work, right? So here it is when we get a little bit further along, right? These are all our temporary shores helping to hold the building in place, right? Notice the little hooks are left on the wall. They can ultimately be removed, but a lot of times they're left as a whole. Another example here of trying to push this into place. Yeah. Right, exactly. So in some cases, there's a bit of a footing that's poured around it that helps hold it in place. Sometimes there's a little bit of a keyway that's done. It varies a little bit in terms of how they do it. Sometimes there's a notch, and I have a video that we'll see in a little bit later that you can see. Sometimes there's a notch where the surface slab here is a little bit higher, right? And then it goes down before the footing, and this fits down inside that notch, right? And then they'll pour a foundation against the outside to help hold it in place. But there aren't those dowels that go up through the building. Yeah. That's the challenge. So you have to think of that as you're now lifting up the slab, so it's going to have a tendency to bend, right, against the lift points. So you have to do reinforcing it on the bottom of the midspan and at the top, right, just like we would do in a building, even though ultimately it doesn't matter because it's all vertical, right? So you end up with extra reinforcing to accommodate that lifting, right? So you're on the right track there, right? So another example here of lifting these into place. Notice again the breadth of the building in comparison to the height of the building, right? This is the ideal type of building for this. And no surprise, it's pretty economical when you have this type of a building, right? Because you're being able to cast these elements without the big wall formwork and stuff, right? Much, much cheaper. So here it is with the steel roof in place, right? It's a series of trusses that are tied together. We'll talk at length about this kind of stuff down the road, but it's enough to understand that you have to have the steel there to help hold the building together, right? And so here's another example, right? You're seeing how large this building is, right? Good example of using tilt-up. We've got plenty of floor space to make our walls, right? We tip them up, and then we have this span. Right? So you already have seen this a couple times, but you're going to see it yet again from me because now we're specifically talking about tilt-up construction, right? This is the St. Ignatius Chapel by Stephen Hull, right? These are those lift points that I was talking about, right? In this particular example, right, different than the one I just showed, the side of the building that's facing out is the side that was up when it was originally cast, which is why those little lift hooks are on the outside, right? And that was something that he chose specifically because he wanted to showcase those, right? And he wanted to show that this was. Furthermore, the way that these pieces come together are not your traditional straight, flat, normal pieces, right? He's played around with the edge of the simple edge form, right, to accommodate where the windows go and how these pieces really interlock together. So yet again, and you're seeing this trend happen with architects or good architects, is their understanding of how the building's going to be made helps inform their design decisions, right? And that feeds back on the process, which is one of the good characteristics of design. So we see it again there with those lift hooks. Obviously, I got to show you one more shot of it. Okay, so this is a video on outside. This is This is in Pittsburgh High School. A couple years ago, we had one of the concrete inspectors.
Everyone is asked to wear orange Friday Deer Valley.
It's a good example.
Please tell everyone you know to wear orange.
That's pretty good. That's pretty good. Oh. Yeah.
So there's also somehow it's helpful to see not just as a video. that are bent over, right? Of course, I start talking right as the video ends, right? Those little extra pieces are what they're going to form that little bit of extra footing on the outside. Okay, so we're going to end there. For next week, you need to read chapter 15, right, which is the precast. It's not quite as long of a chapter. I have some more. There's a lot of pictures in it. So we will discuss that at length. Hopefully it will help you a lot with the pre-tensioning, post-tensioning stuff and help clarify it. So I will see you all next week.